Good morning. We're back. We are looking at chapter 14. We're looking at oscillatory motion. It started out not too difficult, but we've added some complexity. So we've been looking at a number of these examples in terms of the kinematics. How do I keep track of location? How do I keep track of velocity? How do I keep track of accelerations as a function of time? And what we have found is that if we have a force constant with a fixed value of k, that the oscillations, and there's no resistive forces, there's no air resistance, there's no friction, then what we have is oscillations that just go on forever. And we can go in and determine their frequencies based on how much mass the object has and what the k value is for that particular system. So let's go back, and again, I guess I should go back and look at something that represents this. Ooh, all the way back. Boy, it really is, huh? Okay, something like this. So this is another picture that we're going to keep coming back to. We said, you know, if you get confused about some of the things, come back, look at some of these diagrams. So here's what's happening as the objects accelerate back and forth. They're going between plus and minus amplitude. Maximum displacement in one direction, maximum displacement in the other. Those are being represented as minus a and plus a. And then how does the velocity vary? How does the acceleration vary as we go through these cycles? And we went through all that, I think, pretty thoroughly in the last lecture. So I'm going to go ahead and continue moving on. Go back and review as needed, right? So go back and take a look at these earlier diagrams. The diagrams are going to be really handy. We had come up against what looks to be a fairly complicated problem, a little more complicated. We just build complexity as we go. What's going to happen now is, in this example, we've got that same, I hope I have a diagram, there it is. So here's the diagram. It's going to oscillate back and forth, just like that nicely drawn one that we just looked at. This time, in addition to having an initial displacement, we have an initial velocity. So both of those things are going on. And what we said was, we can go back to what are called initial conditions. So that's another thing I guess I could write in my notes here. You guys could write that in. These are considered to be the initial starting conditions for this object, the x naught and the v naught. Those are determined at t equals 0. So t equals 0 could mean when we pull this back and then we give it a push and we start the timer, or it could just be oscillating, and at some point we go, okay, let's call that t equals 0. Right then, right that instant. Either way, these could be written more generally in terms of a cosine function with a phase constant, or an additional phase angle, where phase is telling us where we're located in the cycle. So at t equals 0, and again, you've got to write that in too, I guess, t equals 0, this omega t drops out. And so the starting point is given by amplitude cosine of the phase constant, and the initial speed is given by minus omega a sine. Now, they've told us what the values are of x naught and v naught. We can use those to determine what the amplitude will be and what the phase angle will be. So let's write those down. A cosine of phi, that lower equation, is equal to minus v naught over omega. And omega we already know. So they gave us the mass, they gave us the k value, the force constant. So we know what those are. We can determine what omega is, and we did. The omega was 8.083 radians per second. Here is a sine, here is a cosine. Now, once you've got, these almost look like components of something, right? A sine factor, a cosine factor. We know algebraically how to deal with that. What we can do is we can square this equation, add them together. So that's what I've done. I squared this one, I squared this one, added them together, factored out the a squared. Inside I'm going to have sine squared, cosine squared. So always, get out a piece of paper, go through the algebra, go through the derivations yourself. Looking at a derivation is not the same thing as doing the derivation. So you've got to go through these derivations on your own, make sure that you understand what the steps are between them. Science, engineering, these are not fields where you kind of watch someone else go through the steps. This is where you get in and you carry out the mathematics. Right? You've taken all those math classes, and so this is another class where you get to use, these are the classes where you get to use all that math. So practice these. You square each one of these, you add them together. The sine squared plus cosine factors out. That gives us a way to calculate A. That's a standard algebraic trick for finding out that coefficient out in front. And for us, that coefficient out in front is the amplitude. And this is a good formula to keep track of. So, highlight this and say this is my formula for finding the amplitude for a particular set of x naughts and v naughts. If somebody gives me x naught and v naught, mass and force constant, I can determine omega, plug the numbers in to this, that will tell me the amplitude, that's reliable. Now the other thing we could do, or the other item we need to calculate, is the phase constant. How do I determine the phase constant? And coming to these are kind of our setup formulas. I've got one in terms of sine, one in terms of cosine. If I want to eliminate a common factor out front, I divide these equations. So I'm going to take the first equation and divide through by the second one. That will cancel out the a's and leave me with a tangent of the phase angle. So tan of the phase angle is going to be given by minus v naught over omega, and I wrote that in, divided by x naught. Now this formula we said is completely reliable. I can put in the v naughts and the x naughts. Notice these are squared, so if those signs reverse, it doesn't affect the calculation of the amplitude. What that means is I could have started it at plus 10 centimeters and given it an initial velocity of negative 40. Or I could have started at negative 10 and given it a velocity of, I could have pushed it in this direction, right? Negative 10 is closer in. Let me be clear about that. So I could have started here and given it an extra speed and push in this direction so that it travels out to here. So any combination of plus and minuses on those 10 and 40 numbers is going to result in the same amplitude. Now the phase shift, or the phase constant, or the phase angle, I'm calling them all three, is a little more complicated. And so we have to step a little more carefully here. There's a minus sign here, but remember the functions can't tell us if the minus sign is here or here. It could be that the numerator is positive and the denominator is negative. So in carrying out this problem, we're going to have to step a little more carefully. So let's do that. So here is the tangent calculation, the tangent of the angle. And so I've written everything in. I got all the signs, the minus signs canceling. The tangent of phi is equal to 0.495. Now that much is reliable. But now if in my calculator I do an inverse tangent, it gives me 0.46 radians, which I then converted to 26.3. Then I have to ask, is that the right phase angle? It turns out it's not, and here's why. If I go back to the unit circle from my trigonometry class, so these are so handy, right? What we've got is this. I've got a phase diagram keeping track of what that phase constant will be. Now if I write a cosine in this direction and a sine here for this first quadrant, that would say the phase angle is somewhere between 0 and pi over 2. 0 and 1/2 pi. Now in that region, a cosine theta is a positive number and a sine theta is a positive number. But wait a minute, in this problem, a cosine phi is equal to x naught, and if we look at the problem, or if we look at the numbers that are given, x naught's negative. So x naught is a negative number. Now V naught is positive. But notice from those formulas, A sine phi is going to be equal to negative V naught over omega. So V naught itself, positive, omega, positive. But there's a minus sign out front. That means that both of these components are negative. Okay, both of those values have to be negative. I'm not in the first quadrant. That would be the positive quadrant. I'm here. I'm in the negative quadrant. So cross that out and put the components back here, negative and negative. So that's why this is not the correct one. What we have to do is add on an additional pi radians. I know you want a calculator that just tells you this, right? So there's got to be calculators that do this, where you put in the individual values, the A cosine and the A sine, and the calculator determines, am I in the first quadrant or am I in the third quadrant? That's the third one, right? And then the other ambiguity is between the second and the fourth quadrants. So I can't tell if I'm here or here, and I can't tell if I'm here, or those could get mixed up. So you got to be careful with these phase constants. So I had to, by hand, put an extra phase shift of pi. So I could write this as 3.57 radians. I didn't need the 3, I could drop that. 3.57 radians, or 205 degrees. Now 205 degrees, or 3.5, is going to bring me around to here. Now the other way I could do this is I could write this as a negative value going back the other way, because having a phase of 205 degrees in this direction is the same thing as having a phase of negative 155. Either one of those will give me the same value. So with cycles, we have to think in terms of one complete cycle, and then again, the phase angle could be represented as a positive phase angle. In that case, it would be 205 degrees, or more specifically, more correctly, 3.57 radians, because this is in radians. And then this would be minus 155 degrees. So now these are radians that we're using, and the reason we can tell they're radians is this. Remember omega? What were the units on omega? Radians per second, right? So the omegas are going to come out in radians per second, and that means that omega t has units of radians. And that means this needs to have radians too. We did some of these calculations, I guess, in the previous lecture, and I want to point out now, and I don't think I pointed it out then, that make sure your calculators are set to radians when you're doing these problems. When you're setting up these formulas for position, velocity, acceleration, everything inside the sines and the cosine functions, those are all in radians that we're working with. So if you've been having numbers that don't match up with your sines and cosines, always go back and ask yourself, I probably need to be in radians, right? So definitely here you do. Okay, and so we were able to use, this was a little trickier. Again, what I'm going to claim is that getting the amplitude formula is not such a big deal, but getting the phase angle, you've got to pay attention to what's going on here. So we did get the angles figured out, and again, it's the radians value we want to use. Oh no! Where's the amplitude? Was that on the one before? Oh, we got to go back and calculate amplitude. I'm going to have to go back and do that. I did at one point, somehow it didn't get into the final version here. So the amplitude is going to come from, from that formula. So go back, and it's got to be more than 10 centimeters. So make sure when you calculate this, it's coming out as something larger than 10 centimeters. I think what happened is let me look real quickly and see if I can find that other set of notes. There it is. It just got shifted by 1. So these are a little bit out of order. I'll get that corrected. Okay. All right. So it did slip into the wrong location. So the amplitude here then, we're still back on that previous example. There's the formula. Here are the numbers. Now at this point, I've got the minus sign in here, but everything's going to get squared anyway. Turns out that the amplitude is 11.2 centimeters. Okay. So a little more. Now, I was thinking it might be a little bit more than that, but it turns out it's not that much larger than, so the spring is kind of stiff. Is that what's going on here? Anyway, it didn't go much farther from the 10 centimeters. It only went a little bit farther. And then here is a graph of what one of the cycles would look like. That's what a cycle looks like. Within that cycle, where is t equals 0? Right? So what we found now is that the amplitude of the oscillations is 11.2 centimeters. The frequency of the oscillations we found earlier to be 8.08 radians per second. And let's go with that phase angle of minus 2.71 radians. What was the other version of that we had? It was either negative 2.71 or positive 3.57. So what this is telling us is that if this is one cycle, now that's an entire period in terms of time, but you can also think of this as representing 2 pi radians. One cycle equals 2, how do you do pi? 2 pi radians. And so if this represents 2 pi radians, then this would be the 3.57? 3.57. So this is the 3.57 radians to here, and this is the minus 2.71 radians to here, and that's where t equals 0 would be located. Okay, so I can take a full cycle and find out at what point in the cycle are we starting the timer. So the stopwatch gets hit right there. Those are the x naught and the v naught values. So these are tricky problems. So slow down, and I think there's a homework problem or two on this. Slow down and look at this example. Practice going through some of the derivations for this. All right, now let me go pick this up. This is, now we're ready to start looking at energy. So we want to be looking at energy in the simple, they keep reminding us it's simple, simple harmonic oscillator. And the energy that's stored in the spring is 1/2 kx squared. We've seen this, we've gone through this back in chapter 7, right? Yeah, chapter 7 or 8, we went through and calculated the potential energy stored in a spring. I think in chapter 7 it was calculating the work, and then in chapter 8 we started calling that potential energy. Now the total mechanical energy, we're going to use big E for this, is the kinetic energy plus the potential energy in the spring. Now, if the oscillating system is isolated, then that should remain a constant. If there's no friction, no energy dissipation taking place, then this value should remain constant. So the total mechanical energy will be conserved if there's no friction, no air resistance, that sort of stuff going on. So here we go again. So here is that picture that we said, keep coming back to this. Now they're doing this in terms of energy. So at full compression, at full amplitude, the energy is entirely potential energy stored in the spring. The spring is as compressed as it ever gets, and the velocity is 0. So at this point, we have these little bar graphs. It's all potential, none of it's kinetic. By the time the object has oscillated to the equilibrium point, no, it's moving, it's not going to stop there, but right as it passes equilibrium, all of the potential energy is gone. It's all kinetic at this point. Once it reaches full amplitude in the other direction, it's back to being potential. So you can see how the oscillating systems are great for thinking about potential and kinetic energy, sloshing back and forth, right? If you listen closely, you can hear it slosh. But it's great for seeing how potential and kinetic energy can rapidly go back and forth, because we've seen some high frequencies. And so the energy is switching back and forth between potential and kinetic at those very high frequencies. Okay, so I feel like we've set this up pretty well. So again, as we're going through equilibrium here and well, here, all of it's kinetic. Now, what they've done in that last drawing is they've shown a point in between, intermediate, between the equilibrium point and the amplitude. And at that point, the energy is shared. So if we're somewhere in between, well, the energy is going to be shared between, some of it will be potential, some will be kinetic, but it will still be a total amount of 1/2 Ka squared. So that's one way we could write the total energy, is look at picture number 1 and say at this point the energy is 1/2 Ka squared, and none of the energy is kinetic, so the total energy is given by that value. Okay. So what we can write there, what we can write from this is that the total energy is given by 1/2 K amplitude squared. Now, the total energy then is a combination of the kinetic energy at any given instant plus the potential energy at that very same instant. So that's in terms of variable x, and this is in terms of variable v. Now, what they've done here is they've taken this equation and they've used it to solve for the velocity as a function of time. And that's fine. This enables us to go through and keep track of how fast it's going as a function of position. So rather than velocity as a function of time, what's the velocity as a function of position? So Vmax squared is given by K over m times a squared. And making that substitution, we can come up with this formula. Now, we're keeping track of the total energy as 1/2 Ka squared, but notice K is equal to m omega squared. That's what they're saying down here. So K is equal to m omega squared. This could be written as 1/2 m Vmax squared. And we'll see that, I think, in some of the examples I've written up. So here's another way of graphing what's going on here. Let's say that the vertical axis here is keeping track of different sorts of energy. Where is the kinetic energy? Where is the potential energy? Where is the total energy in the system? Total mechanical energy. And then the displacements are running between amplitude and negative amplitude. And what we could do is we could say, well, the spring energy is given by 1/2 kx squared. 1/2 kx squared would be a parabola. And so what I can do is I can draw my nice parabola for the potential energy. That's what the potential energy is like. Out here it's all potential. Here the potential energy is dropped to 0, but it's a smooth function. It's gradually shifting as it travels from one position to the other. Now the total energy is remaining constant. And we know that the total energy equals 1/2 Ka squared. So my total energy is a horizontal line right here. So that says this red stuff up here never happens. It never comes past that point. And the red line up here never happens. It's not, as it oscillates back and forth, it never goes beyond A and negative A. Now where is the kinetic energy? And the kinetic energy would be the difference. So at any vertical location on the graph, here is a position x. Well, the potential energy is 1/2 kx squared, and the kinetic energy is whatever energy is left over. Okay. So it's a nice energy diagram to think about how the kinetic and potential energies vary as a function of position. This is not giving us timing information, it's giving us position information. Okay, so here's some energy calculations. It's the same spring. It's got a K value of 19.6. The amplitude starting at 10. Oh, the amplitude is 10 centimeters. The function is given as this is A. So this is minus A cosine omega t. So we're starting at that minus 10 centimeter mark. And then we got A, B, C, D. So we need the total energy, the kinetic and potential energies as a function of time. The velocity at a particular location. So they're saying right at the 5 centimeter mark, what is the velocity going to be? And then finally, what are the kinetic and potential energies when x is equal to 1/2 of a, where that's, so that's the same thing. This is 1/2 a, because a is 10 centimeters. See, so this is why, I mean, I recommend writing this as a, and writing this as omega, and then off to the side saying what those values are. Well, we'll see. I've got this written up. I think all that will be included. All right, so first of all, I want to be clear about the potential and kinetic energy formulas. The potential energy in the spring, 1/2 kx squared. And I can write that as 1/2 k. Now, x, for this example, is going to be given by a cosine omega t. Now, I'm a little nervous here. I should have put a minus sign in. No, I dropped the minus sign again, didn't I? Yeah, because they're starting off. Okay, so mine are going to be, now if it turns out it doesn't matter when I'm calculating the energy if there's a minus sign here. This is going to get squared anyway. But I'm starting mine at positive 10 instead of negative 10, just to avoid confusion. And so I can write that as 1/2 k a squared cosine squared omega t. Now, everybody knows what cosine squared functions look like, I hope, because we're going to be drawing some of these cosine squareds. Now, the kinetic energy is given by, at any instant, the kinetic energy would be given by 1/2 mv squared. So I can do the 1/2 m, and then I can substitute in the expression for v. Now, I haven't paid close attention to the signs here. I could say this was supposed to be a minus sign, but it's going to get squared. And I don't need to, because again, we're going to be squaring these. What it tells me is that the potential energy as a function of time is given by 1/2 m omega squared a squared sine. Now I do need a squared there, so that needs to get a square on it. I need to make a note of that. So I need to go down and track down that square sign. So get a square added onto that. And then the total energy, now I wrote this as maximum, the maximum amount of potential energy would be given by 1/2 ka squared. Well, that's the total energy in the system. The maximum amount of kinetic energy would be 1/2 m omega squared times a. If this thing becomes 1, then the kinetic energy would be given by this expression out front. And so that's the total kinetic energy, and that's also equal to total energy. So I just wanted to get the equations written up there. We do need to get that squared added in. And then be clear about how different ways we could write the total energy. Okay, so so in the first part, they're asking us to calculate the total energy. So I'm going to go back and use 1/2 k a squared. This is 10 centimeters, 19.6. I ended up with 98.0 millijoules. Now the numbers here were fairly small. It's a fraction of a meter. And the K value wasn't especially high, so there wasn't all that much energy stored. So 98 millijoules of energy. Now for the kinetic energy and potential energy formulas, what I'm going to do is I'm going to try writing them this way. I'm going to write them as total energy times sine squared omega t, and total energy times cosine squared omega t. That seems handy. These coefficients out front are the total energy. And then I can see, if I add k and u together, what do I get? If I add the kinetic energy and the potential energy together at any instant, that would be adding together a sine squared and a cosine squared. That's going to be 1. And so it tells me that the total energy will be constant. Now, in part C, they're having us look at a time when x is equal to 0.05 meters. And so I put the numbers in. So I put in for the potential energy, 1/2 kx squared. When I know what the x value is, it's pretty easy to find the potential energy. It's not as easy to find the kinetic. So what I did was I calculated the potential energy, that's 24.5 millijoules. Of the total 98, 24.5 are potential, and that says whatever is left would have to be kinetic. So I even went back and plugged this back into my kinetic energy formula to find out what the speed would be. And the speed at that particular value, at that particular time, is going to be 35 meters per second. What was the omega value on this? Okay, I gotta go back and check a couple of those numbers too, make sure that we're good on those. That does look pretty fast, given we only have well, we double checked it in D. So here we go. In part D, x is equal to 1/2 the amplitude. So if I do that, what I would say is that the potential energy then, which the general formula is 1/2 kx squared. Well, for x, I'm going to put in 1/2 amplitude. So I'm plugging in the 1/2 amplitude. Now the amplitude gets squared. So does the 1/2. I squared the 1/2, brought it all the way outside, and put it right there. And then left the 1/2 k a squared in place. Now what that says is, when I'm at half amplitude, I am at 1/4 of the maximum potential energy, or 1/4 of the total energy at that time. All right, and then the kinetic energy then, if the potential energy is at 1/4 of the total, the kinetic energy would be at 3/4 of the total, and that would be 73.5 millijoules. So I can subtract that from the total. These are the numbers that I ended up with. So when we're at half amplitude, you know, a first intuition might be, half amplitude, maybe the energies are shared 50-50, but that's not true, because the energy depends not on amplitude, but on amplitude squared, or on displacement squared. So at a displacement of 1/2 of the maximum displacement, I only have 1/4 of the potential energy. Most of the energy is there is kinetic. And I do have to go back and double check that velocity. How much mass did we have here? It was like 300 grams. I got to go back and double check that. I think I maybe didn't get the millijoules switched. Anyway, you guys check that. I'll go back and take a look at it also on part C and double check that velocity number. All right, moving on with the energy calculation here. So this is a conceptual example. It says this. It says, let's say that we've got something oscillating back and forth. It's got a certain mass, got a certain K value, it's got a certain amplitude to it. What would happen if we double the amplitude? How much more energy would that require for the oscillations to take place? And what we just saw was that the amplitude, or the energy, depends on amplitude squared. And so if I double the amplitude, suppose the spring is stretched twice as far, what happens to the energy of the system? That's 4 times as much. Okay, so doubling the amplitude should give us 4 times the energy. What would happen to the maximum velocity? Well, if we double the amplitude, the maximum velocity and the maximum acceleration, let's jump ahead here. So what we're going to say is that the total energy in the system, 1/2 k a squared, if I double the amplitude, that's what this means, the energy is going to go up by a factor of 4. Now, the Vmax that we've solved for is omega times a. It says that the Vmax would also double, and the acceleration is omega squared times a. If the a doubles, the a max would also double. Now, what about omega? is omega going to change? And omega doesn't. So that's kind of the most interesting item going on here, is that if I pull this back twice as far and let go, how does that affect the frequency? And it doesn't. If I have the same K value, if I have the same mass, then the omega should come out to be the same frequency. Now, how can that be possible? And you go, well, what happens is this. If I pull the block back twice as far, it goes twice as fast. So it can cover twice as much distance. It can cover twice the distance in the same amount of time. You go, oh, that takes care of it then. So if you pull something back twice as far, at each point it's traveling twice as fast as it would otherwise. And so by traveling twice as fast, it can cover twice the distance. Okay? And the same thing with the accelerations. So the velocities and accelerations scale with the amplitude. The omegas are unaffected. So since k is still the same value, m is still the same value, the frequencies will remain the same. So that's kind of interesting to see how changing the amplitude changes the maximum velocity and accelerations, how everything scales. Now, there's this interesting connection, I think we kind of hinted at this before, between simple harmonic motion and uniform circular motion. So, if I'm in uniform circular motion, that means I'm traveling around in a circle at a steady speed. Well, if I take a position along that circle and I divide it into vertical and horizontal components, the horizontal component becomes the cosine of the angle, and the vertical component becomes the sine of the angle. So if I were to take what's called a projection, so if we take circular motion and project onto the x-axis, so as this object goes around the circle at a constant speed, what happens is this object moves back and forth. Its shadow moves back and forth along this line. Now, it's going in a circle at a constant speed, but along the x-axis, the shadow projection is not. The shadow projection is going to start out slower and then go faster as it approaches the center, and that's because you can see the shape of the circle. At first, most of the motion is in the vertical direction. That's affecting the y component. But then it tips more and more. Now it's more and more in the x direction. So it turns out that the projection of uniform circular motion onto the x-axis gives us a cosine omega t function. That's simple harmonic motion. And then if we look at the vertical axis, we can also say, well, what about the vertical axis? Could we project different locations? We can shine the light here and see where the shadow ends up in the vertical direction. That becomes the sine of omega t. So the cosine of omega t is the projection on the x-axis. And here's the diagram. So I'm going to draw it this way. Now the r here should be amplitude, right? So the r that we're talking about is going to become our amplitude. And the theta is going to be given by omega times t. Because if this is in uniform circular motion, then it has a fixed angular velocity. So we're calling that an angular frequency, but back in chapter 10 and 11, those were rotational velocities or angular velocities. So here are my polar coordinates, and this represents uniform circular motion, and look at the x and y components. The x component is going to be a cosine of theta, where theta is omega t. The y component then becomes a sine omega. Those are simple harmonic motion. So there is this fundamental mathematical connection between circular motion and oscillatory motion. All right, we are moving on to a different sort of oscillation. Up until now, we've mostly been looking at springs and masses, is what they're called. So you take a spring, you take a mass, some kind of an object, you attach it, you let the thing oscillate back and forth. What we're going to do in this example, well, with this next series of examples, is we're going to be looking at the pendulum. Now, if simple harmonic motion, you know, the simple wasn't bad enough then, they're doing it again, so they're calling this the simple pendulum. Come on, just call it a pendulum. Don't put the simple out in front. There's all this simple stuff going on in this chapter, and the simple stuff is really hard. So I'm sympathetic. Again, I think this is one of the more difficult chapters, maybe, I don't know, maybe the most difficult chapter in the course. And they're calling everything simple here. So a simple pendulum consists of an object with some amount of mass at the end of a lightweight cord. So what we're going to do the reason this is a simple pendulum is we're assuming the mass of the string can be neglected. Now notice the string has to be sturdy enough that it maintains a straight direction. So that needs to be straight all through the oscillations of this pendulum back and forth. So we neglect its mass, but we imagine that to maintain a straight line. And then here is all the mass is concentrated here, so we're thinking of it as all being located at a center of mass. That makes it simple. Here's the force diagram. So what we're going to do is we're going to bring down a vertical axis from wherever the pendulum is attached. There's the attachment point. Here is the string, or the cord, and then here is the object with mass m, and this thing is going to oscillate back and forth. Now, if you remember, I think we've looked at this with pendulums before, the pendulum is going in circular motion. It's following, it's not uniform circular motion, but it's following a circular path. So whatever distance L is the distance from where this is attached out to where this is, that L remains fixed. So that's kind of like a radius of the circular motion, but it oscillates back and forth along that circular path. Now, the forces we have going on here, we've got gravity which is down. So when the pendulum is at an angle of theta, what we can do is take the mg and divide it into an mg cosine theta and an mg sine theta set of components. So we want to have those as components for the gravitational force, same as we've done before on inclines. Now we're using that analysis on a pendulum. Now there's going to be a tension in the string in this direction, and then the question becomes, where is the restoring force? When we first started out chapter 14, we said oscillatory motion is going to have an equilibrium position and a restoring force. So it's pretty clear. Where's the equilibrium position for the pendulum? And you go, well, equilibrium would be right at the bottom. If we bring the object right to the bottom and carefully place it there, it just stays there. That's where equilibrium is. Where is the restoring force? Where is the force bringing it back to equilibrium? And you might be thinking, well, let's see, tension is not bringing it back to equilibrium. Bringing it back to equilibrium would mean following that circular path. And they've actually labeled it as x. Now that's kind of interesting. They're labeling a curved path, the distance along the curved path, as being x. So we're trying to tie this in with what we've done before. X is going to measure how far away from equilibrium along a curved path the object is located at a particular time. Now x is going to be related to L and theta. In fact, x is equal to L times theta, where theta is being measured in radians. All right, now that says that tension is not restoring the object back to equilibrium. Mg cosine theta is not. It's all being done with mg sine theta. Mg sine theta is the force right along the path. See that path, x, where x is measuring the distance. And the force is opposite direction to x. So x equals 0 is here. They shouldn't have put this arrow here. So x is right here, and x is being increasing. It's becoming a bigger and bigger value of x as we move out. And the force is bringing it back along that very same curved path back to the equilibrium point. So what that says is we have a restoring force, and the restoring force is mg sine theta with a minus sign in front, because when theta is positive, the force is back in the opposite direction. It's back towards the equilibrium point at the bottom. And when theta goes negative, let's say this swings over to the other side, that minus sign is telling us that the force is then bringing us back in the forward direction towards the equilibrium point. So we do want that minus sign there. Now, we got a problem here, and that is that the force is not directly proportional to x. So it's not going to be simple harmonic motion. Let's look at this in a little bit more detail and we can come back. Here's the very same drawing. I left some stuff out which didn't seem to be useful, but I did focus in on this box because this is gravity, and if this is theta, then this angle right there is theta. And that's going to make this side mg cosine, this side mg, and the rectangular box is tipped. So I always feel like that's a point of confusion. How do I draw my vector components with gravity? So it's a good chance to go in and review that. Now, the restoring force we determined to be mg sine theta. The displacement along that path is x, and x is equal to L times theta. So simple harmonic motion, which means using sines and cosines to represent the oscillations, simple harmonic motion would require there be a constant, a force constant with a, some k with some value, where the force, the magnitude of the force, mg sine theta, is directly proportional to the displacement. I can solve for that force constant by taking mg sine theta and dividing through by L theta. But sine theta is not the same thing as theta. They don't cancel out, and so k is not a constant. K varies along that path. So that says we're not going to have something that's exactly a sine or a cosine. Now what does happen, so it's not constant, we don't have simple harmonic motion. What does happen is that sine theta and theta are almost equal to each other in the region where theta is small. So we use what's called the small angle approximation. So coming back to this diagram, sine theta can be approximately equal to theta over a region of small angles. Well, how small do these angles need to be, and what does it mean to say they're the same thing? So here is the small angle approximation. I took this out of appendix A, in the back of the textbook. There's actually a trig table back there. That's kind of quaint to see that. I don't know if you guys have ever looked at a trig table. When I was in high school, we did not have calculators. And so we had to go to a table to look up values for sines and cosines and tangents of angle. Anyway, there's a trig table back there, and it says that for an angle of 5 degrees, the sine of 5 degrees is 0.0872, and you go, well, those aren't the same thing. How can sine theta be the same thing as theta? Well, the thetas here are in radians. So again, this is all coming from thinking in terms of natural units for angles. Degrees are artificial. We've invented those. But radians are kind of built in to angular measurements, as you know from your math classes. So what I did for 5, 10, and 15, and 20 degrees, I converted those into radians, and then I looked at the sine of theta, and look, at 5 degrees, there is only a 0.1% difference between sine theta and theta. Those two functions are almost identical, have almost identical values for the value of 5 degrees. If we move the pendulum angle up to 10, we still have agreement between sine of theta and theta that's less than, well, a little bit more than 0.5%. Once we get up to 15 degrees, the difference is about 1%. and at 20 degrees it becomes 2, and then the differences get larger and larger. What that tells us is that the sine and cosine functions are not going to be exact solutions for us, but they're going to be very, very good approximations as long as we keep the angles fairly low. At 5 degrees, oh my gosh, it's only a 1 part in 1,000 different between the two functions. So if I have a pendulum swinging back and forth just a few degrees, it's going to be an excellent approximation. Now once I get up to 15, 20 degrees, we're looking at 1 or 2% differences. Even there it's a good approximation, right? It's not until the angles get quite a bit larger that the approximations are not as good. Now, I think back in the energy lab, we did a lab on pendulum oscillations using energy conservation, and actually at that time went through, in lab we derived a formula just to give an idea of how to accommodate for that difference. But in any case, we're going to go ahead and just use the small angle approximations. Okay, so for small angle approximation, let's go back and see what we had. I guess this is the best place. So here is now how we proceed with these problems. Notice that I'm talking about a force constant, and there's no spring around. We talked about that in lecture 1, where we said that K, at first, K is going to be the stiffness of a spring, but when we look at other types of oscillating systems, and now we're looking at pendulums, K represents a proportionality between the force and the displacement. So I'm going to define a K, a force constant, as mg sine theta over L theta, and for small angles, using a small angle approximation, I can take the sine theta and cancel them out. So in the limit of small angles, what that becomes is the force then becomes proportional to mg over L times x. Okay, if we go back, we had all those things listed, right? Oh, we got to get the x in there too. I see. And so now what we're going to do is we're going to say that F is equal to K times x. They're putting the minus sign back in. I'm working in absolute values right here. The K value here becomes mg over L. That's specifically K. And then that K gets multiplied by the x to tell us how much force we'll get. Okay, so the little k now, it's not just for springs, it's for pendulums too. So the force then looks like mg over L, where x is given by L times theta. Now, the frequencies, they didn't do the omega. They should have done the omega. I've got it written down. So the periods, they're jumping ahead and writing down periods, formulas for frequencies and periods. Okay, I'm gonna get to that. So I'm gonna come back and show the intermediate steps here as to what the period and frequencies are coming from. What's going to happen here is this: the omega is going to be the k value divided by m, same as it was before. We'll come back to this. All right, so here's a simple pendulum. Here's a chandelier. The cord is being considered as negligible mass. The amplitude is small, and the period's not going to depend on the mass. So for a pendulum, it turns out that the mass effects cancel out. The story is that, you know, that Galileo Galilei in church wasn't really paying attention to what was being said. Instead, Galilei realized that he could use his pulse as a timer. His pulse, you know, was about 1 second, I guess, for each heartbeat. Anyway, the story is that Galilei was in church and there was wind going through the church, and so the chandeliers were swinging back and forth with small amplitude, and that Galilei realized that when the amplitudes were small, they had a certain frequency, but as the amplitudes got larger, they still had the same frequency. So Galilei discovered that the frequency of oscillations is independent of the mass. So let's see why that works. And we'll do that with an example. So what we're going to do is they're going to be measuring the gravitational field. So this is a geologist. So this is a geologist out in the field. And you know, the gravitational field varies from location to location, depending on elevations, depending on latitude, depending on local densities. So this person's a geologist, and they're trying to figure out if there's a locally more dense or less dense region. And you know, they can map that out by looking to see if the gravitational field is a little stronger or a little weaker in a particular area. So they're doing a precision measurement. The geologist gets out that field pendulum, sets it up, and the field pendulum has a length of 37.10, that's 4 sig figs in terms of the length, and it oscillates with a frequency of 0.8190 hertz, and we're going to use that to come up with a gravitational field measurement. All right, here is the picture. Here is our pendulum. Here is everything we talked about before, still set up here. This time, I'm writing this down again. The force is a restoring force, mg sine theta. The displacement is given by L theta. The K value then is given by force divided by displacement. For small angles, sine theta and theta cancel out. And so the effective force constant is mg over L. This is the key step we're adding in. I now take that force constant, divide by m, take a square root, and that will give me the frequency. So those rules still work. Those formulas that we derived earlier are still going to work for us. That's excellent. We can follow the same steps. All we have to do is generalize this step right here, find the restoring force, find the displacement, and then use the small angle approximation. So what that says is that K over m is, reading this formula, if I divide through by m, the m's go away, and I'm left with g over L square root. That's our formula for a simple pendulum. So for a simple pendulum, where all the mass is concentrated together at one location, the frequency of oscillation is going to be given by g over L 1/2. Now, why did the mass cancel out? Why doesn't it depend on how much mass there is here? Well, let's say that we double the mass, or 5 times or 10 times the mass. If I have 5 times the mass, that's 5 times the gravitational force. That means that I'm going to get 5 times as much restoring force. But it's also going to get divided through by the inertial force. So the same thing that we saw before. Remember when we dropped objects and they all had the same acceleration? And that was because if the forces are all gravitational, then the forces are all proportional to mass. At some point in the formulas, that force gets divided through by the inertial mass, and the two cancel out. So if all we've got is gravity driving this pendulum system, then the masses cancel out, and the oscillation frequency is going to be independent of the mass. So let's put the numbers in and see what we get. So we put the numbers in. This was L. This was the frequency that they gave us, 0.8190 hertz. That means that the omega value is 5.146 radians per second, and the period. So I got everything written down. I never put the numbers in. There we go. So on the next page, the omega is given by g over L. G is then equal to L times omega squared. The omega I wrote down as 2 pi f and squared it. So I fiddled around with the algebra. I decided to write it in terms of the frequency. I tend to use omega directly more often, but this time I put everything in terms of frequency. I ended up with this extra factor of 4 pi squared. Now when I put everything in, this was in centimeters, I ended up with a gravitational field measurement, or the geologist did. So the gravitational fields measurement using the pendulum that she brought along is at 982.4 centimeters per second squared. Okay, that looks pretty similar. What we're in the habit of using, we understand that the gravitational field varies from location to location, and we've been in the habit of using 980. So we've used 980. These are in centimeters, not meters. So in meters, that would be 9.80. But in terms of centimeters, yeah, this seems like a perfectly reasonable local gravitational field measurement. Now, one thing we should remind ourselves is the gravitational fields, the little g's that we tend to use, actually, if you remember back in chapter 10, I guess it was, rotation, there's a rotational effect added in on this. So the 980 that we've been using, as well as the 982.4, those are including gravity and the rotational effect of the planet. So if the planet would just stop, we could get a direct measurement of the gravitational field exclusively. This is still including that rotational effect. Okay, kind of cool. You can use a pendulum to measure the gravitational field, which we kind of do in lab. So I think we've done that in lab already. Now, what if the object is not a simple pendulum? What if it's a baseball bat and we drill a hole right there and we use that as an axis? So they've labeled the axis as origin or labeled it with point O. This baseball bat then is oscillating back, and I hope you guys can see the oscillations, right? So we put an axis right here, maybe we put an axle in there and we slide the baseball bat onto the axle and it oscillates back and forth. Anything that's not a simple shaped pendulum is referred to as a physical pendulum. So this is called a physical pendulum, and the difference here is instead of using forces and mass, we have to use torques and rotational inertias. You go, oh, it's chapter 10 all over again. It was pretty traumatic when we went through chapter 10. But anyway, so the torque here is going to be given by the restoring torque, is mg sine theta times a lever distance. And the lever distance here is going to be h. So that's the lever distance. The force became a torque by multiplying by a lever distance. Now, the formula they're giving us here, and we'll go back and see where this comes from. These kind of just come out of the blue in the textbook, or in the, not so much in the textbook as in the slides that the textbook has provided. So now we're going to use a rotational inertia. So the formula has been replaced with that. So let's do that. So now it's a restoring torque. And same as before, the restoring force is mg sine theta, but there's this lever distance. Now the lever distance specifically is being measured between the axis and the center of mass. That is going to be the center of mass. Go ahead and write a cm in there. Those 2 points, the distance between them, is distance h. Now the angular displacement, since it's torques and rotations we're looking at, the displacements are going to be angles. And so the angular displacement it's just theta, being measured in radians. And so what we can do then is we can define a torque constant the same way we define a force constant. So the k value here is going to be the torque, the restoring torque formula, divided by the angular displacement. So I wrote out the torque formula, mg sine theta times the lever distance. Now the sine theta and the theta showed up again, so we said, all right, we know where this is headed. This is one of those small angle approximations. And so k can be given, we can cancel those out. K then is going to be given by mg h. Now this is not a gravitational potential energy formula. This is a gravitational force, but that's a lever distance, not a height. And so the gravitational force times the lever distance becomes the torque constant. And then following up on the very same analogy, instead of k over m, it's k over the rotational inertia. And then everything works the same way. So it's based on the same formulas, the laws of motion, but it's the rotational versions from chapter 10. And so what it says is, hey, that baseball bat, I need to find out how much mass it has. I need to find out what its rotational inertia is. And then I need to measure h and measure the gravitational field of the Earth. And then I can predict the frequency of oscillation for that baseball bat. Okay, and so here's where everything is coming from. So just to go back and review some of that analogy, this is a rotational acceleration, not a linear acceleration, but a rotational acceleration. And that's going to be given by torque divided by rotational inertia. We determined what the torque was. Now the rotational inertia in general, that's going to depend on what the shape of the object is. So I'm going to leave that as a rotational inertia for now. And what that becomes, the acceleration then, see that sine theta? That can be approximated by theta itself. And then this gets brought into this differential equation. The rotational acceleration is the second time derivative of the theta function. So go back to chapter 10. If this doesn't look familiar, go back and take a quick review of chapter 10. This is going to be equal to mgh over I times theta. Now what we've called the stuff on the top is the torque constant. So that's minus k over I times theta. Now that differential equation looks just like the linear oscillation, not the rotational, but the linear oscillation equation. And so we know that theta is a function of time, and that's given by an amplitude. Now the amplitude is written here as theta naught. We could have written it as big A. The textbook used theta naught. I went with that. So this is the amplitude of the angular oscillations, and this cosine is keeping track of how it's oscillating back and forth. Now that says we can get an angular velocity and an angular acceleration by taking a couple of time derivatives. So it's the very same series of derivations. It's the rotational analog of what we've done before. So there's the formula that we came up with. So they've written it now a couple times. This is my angular acceleration. This is the torque constant divided by the rotational inertia. And they've gone through and solved for the period of oscillation. What we did here was solve for the angular frequency. So the angular frequency squared is going to be given by k over I. Okay, so that's kind of the set of formulas that we're working from, and these will work for every system, every oscillating system we look at. These are going to work. Okay, so let's try this. Let's do the moment of inertia. Just checking the time here real quick. I think we have another 5 minutes or so. Ooh, we're closer to end of class than I thought. Let's take a look at this example right here. What we've got is we've got a stick. It looks a lot like a meter stick, except that the center of mass is not at the center. It's actually shifted out to a 42 centimeter mark. Now to be clear, they never said it was a meter stick anyway. They just said it's a stick and it's non-uniform. It's a 1 kilogram stick, but it's not uniform density. So apparently it's heavier on this side and it's not as much mass over. It literally is a stick, isn't it? It's a piece of wood. I see. So I can kind of see the markings now. It gets thinner over here. The center of mass is here. So what we're going to do is we're going to drill a hole in it right there and use that as an axis or a pivot for rotations. And so now we're going to let this thing oscillate back and forth around that pivot point. They want us, they're giving us the period of oscillation. It's 1.6, I'm going to call it 1.60 seconds, and 42.0 saying, I'm going to put an extra sig fig on all this. They want us to find out what's the moment of inertia. What's the rotational inertia? Well, if we look back at the formulas, that looks doable, right? Here are the formulas we derived. It says that I can determine the rotational inertia if I can find the torque constant and if I can measure the frequency, which they've given us information for that. Okay, let's see how this is gonna play out. So this is the formula that we derived for frequency. We're going to flip that around and say we want to use that formula, but to solve for the rotational inertia. It's a funny shaped object, and so let's figure out what its rotational inertia is by determining its k value, its torque constant, and dividing through by the frequency. Now, we went through this with the physical pendulum and found that torque constants for physical pendulums are given by mgh, where h is a lever distance. So the m here was 1.00 kilograms. Earth's gravitational field, looks like part of a parenthesis that we didn't need. Drop that out. The h value, the lever distance, was 0.42 meters. That's giving us a torque constant of 4.116 newtons times meters. Okay, it's a torque constant. It actually has units of torque in it. And so to calculate for I, what we can do is take that and divide through by omega squared. Now, the omega is going to come from here. So they told us the period. We took this. This was in a lab. So we're in lab. We measured the period of the oscillations. They are at 1.60 seconds. And the frequency then we can get is 1 over t, which is 0.625 per second. And then finally omega would be 2 pi times that. So the radians frequency is 3.927 radians per second. Ooh, I didn't really need that either. Okay, I got a number of things I got to go back and clean up. So cross that -1, that's just radians, the seconds are already in the denominator. Putting that number into here and squaring it, there you go. There's the rotational inertia. And so 0.267 kilograms meters squared. Now it would be kind of interesting, you know, the rotational inertia of a stick, a uniform stick, would be 1/2 ml squared. So we could use this to estimate the length of the stick. Might be an interesting thing to go back and take a look at. Okay, now what they also asked us in the problem, I believe, is they said, fine, we have now calculated the rotational inertia around the pivot, around that end point on the stick, but what's its rotational inertia going to be around the center of mass? That might be an interesting place to determine the rotational inertia. What if we want to take this stick and just throw it? It's going to rotate around its center of mass. What would be the rotational inertia there? Now, I know Chapter 10 was many, many weeks ago. It's a distant, distant memory. But the rotational inertia around the center of mass should be lower. And we should be able to use what we called the parallel axis theorem. So, and I could have written that down too. Parallel axis theorem says that if I start with the rotational inertia around the center of mass, ICM, and then move away from that by a distance h in a parallel direction so that the axes are parallel to each other, then the rotational inertia at the end point would be given by ICM plus mh squared. Now we're going to flip that around because we just measured I for the axis at the end, and we can subtract off the mh squared to get ICM. And so the mass is 1 kilogram, h is 0.42 meters, mh squared, this part of the calculation, is going to be 0.1764 kilograms meters squared. So we can take that rotational inertia that we measured, 0.2669 minus, was that what we measured? Oh, I see. We measured 0.267. I rounded a bit. I don't know why I'm keeping the extra. I must be nervous. You guys do that, right? If you get nervous on a calculation, you start to keep more numbers. It gives you a sense of security. Anyway, I went back and kept 4 sig figs here. Oh, I wanted to get 3 in the answer, but that's not. Anyway, minus 0.1764. And I ended up with, this is the rotational inertia around the center of mass. This is the rotational inertia around one of the endpoints. Now for a uniform stick, that would be the difference between 1/12 and 1/3. And so that would be about a factor of 4. For a uniform stick, we would expect that number would be 4 times bigger than that. And that's not, didn't quite measure out. So the non-uniformity is making an important difference here. Anyway, kind of interesting that we can go through and do these oscillations and figure out rotational inertias. Now there's kind of a similar sort of what's called a torsional pendulum, where we can allow a mass, it doesn't have to be disc-shaped, but something where the wire is under torsion. So you can see the angular, the way this thing is oscillating around a vertical axis, and the wire becomes twisted. So in this case, there is a force constant, or a torque constant, and the torque constant tells us how stiff the wire is relative to torsional stress. So, which we saw back in chapter 12. I don't think we have any examples of this, although it's pretty analogous to what we just looked at. But it's kind of interesting to think of, here's a wire, and we can have it rotate one direction, it can twist one way, and then it can twist back the other way, so it can kind of twist back and forth. All right, that's a good place to stop, so we're going to stop there. We're going to move on to what's called damped harmonic oscillations. Up until now, we have had no energy losses, no friction, no air resistance. Now we're going to look at what happens if we put a little bit of friction in or a little bit of air resistance. And what we can see is that the oscillations, the amplitudes are going to drop off. Anyway, I'll go back to here because it looks more friendly. And we'll stop there for the day. So whatever questions come up, stop by office hours. Again, this is a challenging chapter, so make sure you're staying caught up. Make sure you're stopping by with whatever questions.